Let's wrap this module up with a summary and then some quick examples. We know that comma-separated lists of objects occur in three instances: as multiple input arguments to functions, multiple output arguments from functions, and the horizontal concatenation syntax uses comma-separated lists. Certain expressions involving cell arrays and struct arrays are automatically converted to or can be thought of as shorthand for comma-separated lists. A field reference of a struct array is converted to a comma-separated list of the field references to all the elements in the array. A contents reference of a cell array is converted to a comma-separated list of contents references to all the elements of the array. And this generalizes the field references and contents references that we learned initially when we considered scalar structs or a single contents reference. If the struct is a scalar or the cell contents reference is a single element, then the comma-separated list consists of one element and hence 0 commas, which is a normal reference as expected. Let's look at these cases with a few examples. Let's start where we just finished with a scalar struct or a single contents cell reference. S will be a 1x1 struct with field name F, and C an n by m cell. The field reference to s.f, is in general a comma-separated list of field references to all elements of the array in linear order. But there's only one element of the array, so this is s1.f. How about a single contents reference to a cell? Remember, in general, contents references to cells are really comma-separated lists of contents references to all the listed elements of the array in linear order. Here we've only listed one element, therefore this is exactly the single element C of k. This illustrates how the general definitions really are the original definitions that we learned about when we only considered scalar structs or single contents cell references. Now let's go to the other extreme. A non-scalar struct and an all contents reference to a cell array. Let's start with the struct. Remember, in general, a field reference is a comma-separated list of field references to all elements of the array in linear order. What does this lead to here? There is a comma-separated list of field references to all the elements of the array in linear order. In terms of the row and column indices, here the elements are bunched a little bit together, but you see the 1, 1, the 2, 1, the 3, 1, and then the 1, 2, 2, 2, and 3, 2. A comma-separated list of field references to all the elements of the array. For cells, the analogy is an all elements contents reference. In general, contents references are a comma-separated list of contents references to all the elements of the array in linear order. Therefore, this expands to 1, 1, 2, 1, 1, 2, and so on, all the way over to 2, 4. Expressed as single indexing, it looks just like that. Clearly, linear order. Now let's keep the setup the same, but only reference a subset of rows and or columns. For example, here's a field reference to a subarray of the struct array. Just grab those subarray elements in linear order, 1, 2, 3, 2, and do a comma-separated list of the field references to those elements. Here's one using the colon operator, all the rows, first column. Just make a field reference to all those elements in linear order. The 1, 1 element, the 2, 1 element, and the 3, 1 element. For cells, it's very similar. Contents reference to the second row of a cell array. Do it in linear order, C21, C22, C23, C24. Conversely, column reference to all the elements in the third column. Linear order, C13, C23. Lastly, let's end this module, which has gone on for quite some time, with a very useful construction, extracting all values of field F from a struct array S into a cell array C. Well, if you think about it, it's a really simple command. There it is. C equals open curly bracket and then the field reference to the struct array. We know the field reference to the struct array is a comma-separated list of field references to all the elements of the struct array. Placed inside a curly bracket creates a cell array with those as the contents of each individual cell. It preserves the linear order. The concatenation occurs horizontally, and therefore the size of C is 1 by the number of elements of S. This simple line is equivalent to this for loop construction. First, allocate C as a cell array of appropriate dimension. Then loop through all the elements of the struct array, and using single indexing, fill the contents of each cell with the field reference from the corresponding element of the struct array. With one simple modification, the cell array C can be made to have the same size as the struct S. Simply reshape the cell to the size of S. Since this has the proper dimension and the elements are in linear order, this results in C having the same size as S. The for loop version of this is exactly the same as before, except C is initially allocated to be of that proper size rather than the row up above. The same for loop works, just using single indexing not only on the struct, but also on the cell. Remember, for an array of any dimension, single indexing assignment, as long as it's not past the boundary, never changes the size of the array. This means C remains its original size, which is the size of S. That completes our review of comma-separated lists and how they're used in field references to structs and contents references of cells. Most everything you can do with that part of the language can also be done with for loops. Sometimes you might find that easier to conceptualize. In other instances, the very clean and elegant code that will result from carefully using comma-separated lists might be more attractive.